Happy New Year. It's lovely to see such a large and extraordinarily well-informed audience tonight. This looks like the Newcomen Society at its best. In particular, a very warm welcome to members of the Historical Metallurgy Society who we invited along. I can see Justine over there, Justine Bailey, Peter King and Tim Smith. I'm sure there are others who are, perhaps some of you are both members of the Historical Metallurgy Society and the Newcomen Society. A very warm welcome. It's great to have visiting experts. I'd like to introduce Richard Williams, our speaker for tonight. I have almost crossed paths with Richard in the past. He was he's a graduate of what became Brunel University and got a PhD there under Colin Bodsworth. This is probably about the time they rejected me as a lecturer. He then became an export salesman for foundry equipment, and he sold foundry consumables for Seco Minsep, the well-known foundry supplier from the West Midlands, who also rejected me for a job. He then went to work on construction chemicals and spent the last 20 years of his life in the venture capital company.
Working life, I think.
Working life, sorry. Since retirement, he's got interested in developments in 18th century ironmaking, and of course could bring his metallurgy skills. His PhD was on the thermodynamics of iron-carbon interactions, which is absolutely at the heart of iron-making issues in the 18th century. He was able to bring his skills to the subject, not just his skills as a metallurgist, but also he somewhat self-effacingly says that he reads French and German. I'm sure that he also has linguistic skills.
So how did I qualify that?
You did qualify, but I suspect you were being unduly modest. The papers...
With great difficulty as well.
What he's going to talk about tonight is a great metallurgical myths of 18th century ironmaking. Some of you who are members of the Historical Metallurgy Society will recognise a series of articles that he's written in that journal. I'm delighted to say that he's also offered us an article for the Newcomen Journal on a quite different topic. Richard, the floor is all yours.
Thank you very much. Well, I must say it's a great privilege to be here. I mean, this is a hugely important society that you have here, and I'm absolutely delighted to be able to come and talk to you. The story behind my research is that in 2013 I was, I volunteered actually to give a talk basically on this pot, which you will observe was going to be 300 years old the next year. And I thought this would be fairly easy. I hadn't done any real work on it before, but I would simply go into the library at the Cort Museum, and I would read all the books on the subject, because lots of people must have written lots of books on the subject before, and then I would sort of take a few pictures out of the books, and that would be it. Was I wrong or was I wrong? The amount of metallurgy that had been done really on the 18th century ironmaking is actually quite small. And I rapidly discovered this, and then also came to the shrewd suspicion, having looked at what had been done, that not all of what had been done was actually right. So I sort of set out to do what I could. I have to start by making sure that everybody at least understands the very basics of what I'm talking about. So this is a blast furnace, more or less as it would have appeared in the 18th century, with a typical pair of bellows blowing in at the bottom, with iron ore and a fuel, which I'll come back to, and limestone being poured into the top. The whole thing was on fire and ran continuously for months on end. And out of the bottom came pig iron and slag. And the slag was a very important part of the whole process, as we shall talk about it a little bit later. But the pig iron that came out at the bottom was used for two purposes. It was either cast into moulds to make what you all understand as castings, or it was given a further treatment and the carbon was taken out of it, and it became what was technically known as malleable iron or bar iron, but you would understand as wrought iron. The fuel is the essential point to discuss tonight, because for most of the 17th century, the fuel that was used in blast furnaces throughout Europe was charcoal made from wood. By the end of the 18th century, in Britain, and nowhere else really, but in Britain, most of the iron that came out of blast furnace was actually made with coke, which was produced from coal. And that's really a key part of everything that went on in Britain over the 18th century, as all the individual iron-making processes were converted from charcoal to coke. So we'll start with myth the first, because it's a very good way of starting. Dudley lied when he said in 1665 that he had successfully made iron with coke. Now he claimed to have made iron with coke with coal actually, to be fair. He never actually specified coke. In the 1620s, and he went on to build 3 furnaces, one after the other. People have basically questioned whether Dudley actually did what he did, because he was known to be a bit of a bounder and was a bit prone not to telling the truth. But we must start with one of his, an excerpt from his Metallurgical, 1665, which was written essentially to obtain finance for yet another attempt to make iron with coke or coal. The interesting thing about this is he introduces the theme of grey and white iron. Actually, this is the first time that anybody in the Western world has ever written about grey and white iron, and he gets credit from it for outside Britain. Doesn't get quite so much credit within Britain. Agricola didn't write about it, Theophilus didn't write about it, Biringuccio didn't write about it. Dudley was the first. And he showed in doing this that he actually knew a lot about iron. But in this statement, that I'm sure I hope you can all read it anyway, is it clear from the back? There are basically three truths and one lie. The 3 truths are, yes indeed, there were 2 kinds of iron that came out of the blast furnace, and indeed one of them, the grey iron, was more likely to come from a coke-fired blast furnace than from a charcoal one. And indeed, that the grey iron that came out was very good for making castings. The lie was that it was also good for making bar iron or malleable iron. And that was really his problem, I think, because in those days, the malleable iron side of it was by far the largest part of the market, and he wasn't really going to be able to create a business unless he could supply that market. So he basically, his efforts basically came to nothing. And there's a lot of history behind it, which I'm not going to go into. So these 2 very different metals, white iron and grey iron. I'm not going to repeat what's up here, but basically, they were almost opposites. One shrank and therefore wasn't very good for making castings, whereas the other one could even expand slightly. That was very good for making castings. Whereas the white iron was much better for making wrought iron. I use the term wrought iron so that you know what I'm talking about. And there are all sorts of other chemical differences that arose. And one of them that I'm very fond of is the fact they make different sounds. Providing I get the right one, you'll know what I'm talking about. You all hear that?
Yeah.
It's not a bad sound, is it? Now this was made by a Swiss company as a giveaway for the Japanese market. And it was given to me by a man who I used to work with at Fasico, who subsequently worked for George Fisher, and is now actually a trustee of the Iron Library, which I have frequented quite often. He gave it to me. Oops. I came back to the UK and I had a copy made at the Ironbridge Gorge Museum Foundry. But of course that's grey iron. That's white iron and that's grey iron. The reason why this one's so dull and this one's so bright is that in a white iron, the carbon that was dissolved in it, 3.5% of carbon that I talked about at the last furnace, came out as iron carbide. Whereas in a grey iron, it came out as graphite. And the graphite is, of course, a very good absorber of vibrations. So that's why the things are different. They're both magnetic, so I won't be able to show you that. I'm sure all of you recognise the yoke that's on it. I haven't actually switched to the next slide, I should have done. Everybody recognise what this is?
Yes.
Yeah, that's it. Well, in 1967, the new Brunel University was handed over from the builders to the university itself. And at 9 o'clock that morning, I was knocking on the door to get in, because I'd been sitting for 6 months at Acton waiting to start my research. And that day, I went for a little walk, because there was nothing else to do, there was nobody else to talk to. I went off and went for a little walk, and by complete happenchance, I'm sure it wasn't deliberate, they built Brunel University alongside the railway line between Uxbridge and West Drayton, which had been a broad gauge railway line built by Brunel. And they discovered a fence post holding up the fence to stop people going in, which I thought I knew. And I picked it up, half-inched it, took it back to the foundry, where I half-inched it again. So I thought that's quite nice. Talking about the white and grey iron, now if you mix the two together, as you can do, then you get what's known as a mottled pig. Well, that's a mottled pig. A bit more personal history. I used to breed saddleback pigs. Now then, the thing about this whole question of grey and white iron, which is very important, they're coming to the point, it's very important for the development throughout the 18th century, was that there was a chemical tendency for an iron to turn white or grey, but whether it did or not depended on how fast you cooled it. And this carbon equivalent gives you a very good measure of whether the tendency for an iron to turn grey, in fact. There's a well-known test, modern test, for checking how grey or white a cast iron is. You simply cast a wedge, and you cast it in sand, just use a standard pattern. And you can see here, at the very tip, where it's thin, is cooled quite quickly because it's thin, and it's turned out white. But the thicker sections turned out grey. Now, these microstructures you won't be able to see, I'm sure, from where you are, and you probably wouldn't be able to understand what it was anyway, because it's very unclear. But in the white structure, you've got alternate lamellae, basically, of iron and iron carbide, whereas in the grey iron, you've got the graphite coming out in various forms, but in the 18th century, most of it would have come out as what's here labelled type A. In a blast furnace, you've got a tendency to pick up silicon. First of all, you have to reduce it from the silica, and then it has to get into the iron. The phosphorus that was part of that equation actually came from the ore and had nothing to do with the blast furnace as such. Anything that was in the ore came into the iron. But in the conditions that really enhanced the production of a grey iron, behind the increase in silicon, was first of all an average high temperature in the stack. Secondly, the longer it was in the blast furnace, the greyer it became, and the presence of high activity silica, that is silica that hasn't got lime or something to counter its acidic tendency. It's can, in sort of the thermodynamic terms, the activity will be reduced. If you have lime present, then the temperature at which silica can be reduced actually goes up. In the standard state, the temperature you need is something like 1500 degrees centigrade. But on the other side, the fact that you only want your silicon in the iron at sort of 1 or 2% means that actually that reduces the temperature at which you can reduce silica. Now, charcoal furnaces, they could make grey iron, but only up to a point. The first thing was to keep the iron in the furnace for as long as possible by using a high fuel to ore ratio, which you happen to do when the thing started up anyway. So if there was any tendency for your ore to produce a grey iron, then when you started up the furnace, you'd get grey iron out of it. And when the ores were difficult to reduce, you'd get the same sort of thing. And then again, you needed this presence of silica without the lime or magnesia. But coke furnaces just produced a grey iron naturally. They did work at a higher average temperature. We're going to come to that later. The burden spent nearly twice as long in the furnace as it did in a charcoal furnace because of the characteristics of coke. But then, and I put this in red because this in a way is breaking a myth. It hasn't actually been noticed in the historical context, but there's been a lot of work in blast furnaces basically since the war, where they've shown that an enormous amount of the silicon in modern blast furnaces actually comes from the ash in the coke. And you have the perfect conditions in coke. You've got the highest point of temperature, you've got the silica and carbon intimately mixed together, and it's got to be solid-solid reaction. So actually, the coke was probably responsible for more than anything else in making sure that, as Dudley said, you would get grey iron from a coke-fired blast furnace. Just to emphasise that although Dudley was the first person to write about the difference between grey and white iron, they must have known for years before that about the difference. And the basic thing was you broke your iron and you looked at it, and if it looked white, it was white iron. If it looked grey, then it was grey iron. These castings were found at an American ironworks. It was only in operation for about 6 years. 6 years? 9 years. 8 years. The great thing about that was, of course, that it was abandoned, and therefore when they came to excavate it, they got an awful lot of interesting stuff there that you would not tend to get in a ironworks that had been going for a long time. And they found these castings all near the blast furnace, most of them broken. And I think you can probably guess that these were, this was one way of telling just how grey or white your iron was going to be. Now, Sorgus was a charcoal furnace, so, but you can tell that they were pretty sophisticated in those days. So I'm going to move on. Myths 2 and 3. Abraham Darby was the first to smelt iron with coke, 1709, and he invented and patented the green sand moulding process in 1707. Neither of these are true. It's all about the manufacture of pots, and pots are thin. And if you think that this wedge, probably there you can see where I've drawn 5mm on it, is about the thickness of a pot. If you're not careful, your pot is going to come out white, and that would be a bad idea because white iron doesn't pour very well. White iron shrinks by 5%. That would mean you'd have difficulty getting it out of the mould. And even if you actually succeeded in getting out of the mould, you'd be doing your cooking with something that was akin to glass. So the important thing was to make sure that if you were going to cast a thin pot, that you cast it with the suitable iron. And these are recommendations for the carbon equivalent for progressively thicker castings. Made in about 1911 actually, but American by the name of Morlenko. The important thing about this was, if you wanted the maximum strength from any iron, then you actually had to match the composition to the thickness of the casting you were making. Ideally, to get the maximum strength, you wanted a casting that was just grey, not too grey. If it was too grey, then it would be weak because the coarse graphite flakes you have would act as a path for propagation of cracks. And of course, if it was white, then that was not what you wanted. So you actually had to be pretty precise as to how you were going to, what quality of iron you were going to use for what quality of casting. Analyses of old iron castings are actually few and far between. They're a bit like hen's teeth. But this little book, which was written in 1948, produced lots and lots of analyses of the of various castings made throughout the 17th, 18th and 19th centuries. A pair of Belgians, and they were writing on the 400th anniversary of the Usine des Veines, which is quite a nice long history going back. And these are the results that Desky and Edvard actually published. And as you can see, they separated their castings into 3 thicknesses. So, starting at the bottom, heavy section castings, greater than an inch, 25 millimetres, medium section casting, and then pots at the top, which were less than about 5 millimetres. And actually, if you go back to that table in which I listed Moldenka's recommendations, then the bottom 2 are actually quite accurate, but the top one isn't. Moldenka said you needed 5% carbon equivalent to manufacture a thin pot. And these people seem to get away with less than 5%. And Edvard Desky recognised that these castings should not have been grey. But they were grey because they looked at them under a microscope. They argued that there was no way that these moulds could have been heated, because that would be one way of slowing it down and getting the grey iron. So they looked for some sort of chemical cause, and they weren't very convincing in what they came up with, I have to say. It's not really surprising, because they were French-speaking, and had they looked in this Description des Arts et Métiers, which was not the Diderot encyclopedia, this was another one that was produced by the Académie Royale des Sciences. And one of the leading lights in this description was Réaumur, who we all know was probably the leading scientific metallurgist of his day, throughout the 18th century probably. And if you look here, he's quite unequivocal about it. You heated the moulds, and it depends on how thick your casting was and what sort of iron you were casting. So they did heat them. But if you're going to heat the moulds, you had to use a particular casting process. You had to use the loam moulding process. And loam moulding is basically where you use a substantial amount of clay, 25 to 50% perhaps. You mix it with sand, you mix it with organic material like horse manure or something exotic like that. And then you treat it as if you were making a sort of ceramic pot. You can basically smooth your mould. And they used a strickle board to make first of all, the inside the core. Then they used a slightly bigger strickle board and put a thin layer on top of that, a thin layer which wasn't quite so strong. And that was actually to form that was effectively the pattern, that was where the metal was going to go. And then they covered it over with clay to finish the job and put on the feet and the ears. And this is a picture of it was a woodcut, I think, that appeared in that book that I was talking about. And although the book didn't come out until 1761, this was made in 1718, and so was this one. Because what happened after you made up that sort of mould, you've still got your pattern, in inverted commas, inside, you had to cut it. And you cut the whole thing in half. Vivian showed you a knife here. They cut the whole thing in half, cracked the thin pot shape off the core, put the thing back together again, stuck it together with clay, and then fired it to a high temperature. And they fired it to a high temperature, first of all, to make sure that it was nice and hard, but secondly, to burn out that organic material that I talked about, so that you got a fairly porous mould to allow the air and the gases to escape from the casting. So actually, all you had to do to pour your metal into a hot mould was take it straight from the firing process to the moulding station, to the pouring station. And then you can always recognise a low moulded pot because you get this line going all the way underneath it, which you can see there. I think it's quite clear on that one. And this is actually one of the pots that Everard Adesi analysed. It's at the Maison de Metallurgie in Liège, which is a wonderful little museum. It's quite a small museum. I was once asked whether it would be possible to analyse that pot, as I showed you earlier, the 1714 pot, without damaging it. That was Everard Adesi at work. I brought that back to the then curator at the Ironbridge Gorge Museum and said, "This, I can do it with, you know, providing you let me do this to your pot, that'll be fine." Now the point about this was this is the first cast, the oldest coke iron casting that we know about. And when you examine it, it hasn't got any trace of parting line going underneath. In fact, you can't see a parting line on it anywhere. And the reason for that is it was cast in sand with a wooden pattern or a brass or iron pattern, and it just needed two halves to make it. And the parting line is, of course, along the bottom there, so it's along the top of the pot, and you can just easily file it off. So it's not obvious, you don't see it. Now then, the logic of all that is that you could cast pots in sand, but only providing you used a coke blast furnace. If you had a charcoal blast furnace, you had to make your pots in loam. Now you can just begin to understand that it was much cheaper to make pots in sand. So, we can play a game of follow the pots. And Peter King, who I'm happy to say is in the audience, is responsible for all this work, which is absolutely terrific. If you hear a snort, or a gasp, or an expression of anger, then Peter will perhaps explain later. But it's terrific work. So, in his first paper, he pointed out that Thomas Addison had got a patent for coke in 1692. The company for the manufacture of iron with pit coal, sometimes the company for the running of iron with pit coal, was incorporated in 1693. And the three of them, of the directors, members, were Addison himself, Shadrach Fox and Thomas Fox. Now Shadrach Fox is known to have had the furnace at Cobra Bailey before Abraham Darby. And it's known that, Peter picked it all up, Shadrach Fox sent a shot, and both hollow and solid shot, to Bristol from Cobra Bailey, both in his own name and in the name of the company for the manufacture of iron with pit coal, from 1693 onwards. Addison used coke at Cleator, I'm not sure how it's pronounced, in 1694, but that wasn't very successful. And Peter deduced that Shadrach Fox had been using coke in his blast furnace not only because of the obvious connection, but because at some stage he had to assure the Ordnance Board that he was not contravening Addison's patent, or at least he had Addison's agreement to use it. So then we move on into the 1690s, and Peter has got all of this from a fantastic legal document which explains the whole thing in huge detail and absolutely perfectly. There was, in 1695, a Roger Downes who worked for Shadrach Fox at Cobra Bailey, and he was described as a man skilled in the art of making pots in sand, or at least casting in sand. The same year, there was a Thomas Cheadle, who had a patent, not sure if it was ever granted, but certainly he filed for a patent using coke. 1700, Shadrach Fox's furnace blows up. We all know about that. It's well sort of documented in most books on the life of Abraham Darby. And Downes came to a gentleman by the name of Zachary Downing in a rather distraught state. not immediately, one suspects, from the explosion, but having not done particularly well for himself since. Shadrach Fox went off, and I won't go into the detail of what happened to him. But Downes approached somebody called Zachary Downing, who had blast furnaces at Cradley and Hales, and he worked for Downing making pots in sand at Cradley. At the same time, he went off for a period and spent some time with Chittle, who had an iron blast furnace at Gwendraith in South Wales. Then we sort of integrate this with the Darby story. Darby, as I'm sure most of you will know, set up a test foundry in Bristol where he didn't have a blast furnace, he was just remelting iron. And he developed his sand moulding process there. And Downes met Darby around about 1708 and sold him patents from, which he'd got from Cradley, where he'd left some time ago. The court case was all about whether he was actually in a position to provide those patents to Darby, because Downing argued that they were his, and Downes argued that he brought them from Coalbrookdale in the first place. Darby said he didn't really need them, but he just sort of liked to take them off the market, I think. Anyway, so Downes then works for Abraham Darby. When Darby moved to Coalbrookdale, eventually Downes went with him, and Downes's employment at Coalbrookdale is widely acknowledged in the accounts that are known, that are still in the Shropshire archives, working for Darby at a somewhat inflated salary, I think. But then there's the question that Darby patented moulding pots in sand, despite the fact that the whole thing had been done beforehand. But he didn't. He actually patented a way of casting bellied pots and bellied ware in sand. And to do that, he basically needed a slightly different kind of mould. He needed to have two sections which moved sideways to enable him to get the pattern out from the space that was where it was. And this shows you how basically it was done. This is the result. Now you can't see that absolutely perfectly, but there I show you there is no line going under the pot. What I can show you is a crummy pot with much more clear parting lines. And of course the parting lines are there and there. And here is a special moulding box just designed to do exactly that. And you can see how it's got the iron castings which, whoops, sorry, move sideways. And there's the follow the pot's tube. Isaac Wilkinson designated himself a pot founder, and he worked at Little Clifton sometime before 1735. Little Clifton was, I think, built in about 1723, and it was specifically built to use coke. He then moved to Backbarrow, where he worked for another sort of 13 years, still apparently making pots. Now there is no known record of Backbarrow using coke. There is a letter, famous letter, sent from Abraham Darby I to one of the partners at Backbarrow, suggesting that he might like to use coke, but that was long before. But there is no known record of Backbarrow using coke. In 1753, Isaac Wilkinson took over the Bersham furnace, and the Bersham furnace alternated each month between charcoal and coke. Now we don't know that Cradley ever used coke. There is no record of Downing ever using coke at Cradley. So we've got two works that somehow made pots in sand, which suggests that they were using coke, but there is no record that they ever did so. But perhaps there's just a little bit of a hint that if you can switch between coke and charcoal alternate months, then you can specialise in both iron for the forges and iron for castings. I just want to finish this section on Abraham Darby by just really emphasising just how sophisticated the iron foundry business was in 1700, because this is an advertisement that was placed in the London Postman newspaper in December 1700. And I don't need to read it out for you, but the important thing here is that this was a remelting foundry. It didn't have a blast furnace. The suggestion is that, well, without wood, charcoal or bellows, it had to be using a reverberatory furnace, which was a furnace that was fired by coal and just had a natural draft using a tall chimney. And you can see the level of goods that they were manufacturing. This is the first of the list. And they look to me to be pretty sophisticated. You've got bells and pots and kettles. You've got rolls. You've got rolls and backs and hearths for chimneys and so on. Goes on. Hatters' battens. I presume that people used iron formers to make hatters. I'm not sure what plates for packers are. You can perhaps imagine that they were some way of sort of getting, consolidating, I don't know, something into bales or something. Hot presses where they made cast iron smoothing irons. Very large plates for looking glass grinders. Oh, that's quite a fascinating sort of thing. Cylinders for waterworks. Those were pumps. They were producing cast iron pumps in 1700. Boxes for coaches and for anvils. These were some of the few applications for white iron. They did make white iron castings, but only where they desperately needed wear resistance. And the boxes for coaches are basically the bearings for the axles, where you would need, obviously, quite a lot of resistance to wear. And anvils had to be pretty hard and pretty strong. And then finally, they talk about the iron, clearly making white and grey iron. The bit I like at the bottom is the best founders in loam and those that can mould in sand will find encouragement with all necessary provisions of life. They wanted sand moulders and loam moulders, and presumably they wouldn't be advertising unless there was quite a lot of other foundries around in the area that had workmen like this in them, and this was just a London paper. Okay, we move on. How am I doing for time? Not too bad. Myths 4, 5 and 6. These are all interconnected. So a coke blast furnace was naturally hotter than a charcoal one. That's everybody just takes that for granted nowadays. Actually, I don't think it was. But the logic seems to have been that they assumed that this was the only way in which you could actually get your silicon into the iron, by having a high temperature. Then you read, as you go through all the history, that people increased output simply by increasing the amount of air that they blew in. Well, that didn't work, actually. If you blew in more air, first of all, you changed the quality of the iron that came out. And then finally, if you continued to blow in more air, you eventually got unreduced ore coming to the bottom of the furnace. And this is all of relevance what Abraham Darby II did when he got pig iron into the forges. And this was a very significant event, because before 1755, just about all the iron that came out of the coke-fired blast furnace went into castings. It wasn't possible to use it. I have to be careful there, because it became increasingly possible to use it. But initially, it was not possible to use iron from the coke-fired blast furnace in order to make wrought iron. Just for use for casting. And then suddenly, 1750s, it exploded. Abraham Darby II built 4 furnaces in the space of 2 years, and lots of people copied him. And everything that was coming out of here, almost everything that was coming out of here, went into the forges for turning into wrought iron. if we examine that, people have said that nobody has ever got to the bottom of this. There have been theories, and they've talked about it a little bit. There was a gentleman called Hyde, who was an American, said it was just a matter of economics. He's been substantially disproved. Various authors assumed it was down to the high silicon content. It couldn't have been down to the high silicon content because they cheerfully made iron on the continent out of quite high silicon content pig iron, and subsequently, of course, they did it in this country as well. Mr. Mott thought that it was all down to phosphorus, and that Abraham Darby had selected special local ores with a low phosphorus content. But that doesn't stand up either, because basically, you know, that was exactly the problem that the charcoal furnaces had anyway. It was undoubtedly down to sulphur. And Swedenborg, who was in Britain in the sort of 1720s, 1730s, said quite plainly, you know, and he knew what he was talking about, it's down to sulphur. You can't use this newfangled coke-fired coke iron in the forges, because the sulphur makes it very, very brittle at high temperatures, what they call hot short. And that's absolutely right. And when you've got a lot of sulphur in your iron, you get a low melting point phase which comes out at the grain boundaries, and when you hit it with a hammer, it all flies to pieces. Tilcott was the nearest modern person to get to it, but he didn't tie it in with Abraham Darby's successes. When you want to remove sulphur, you need to have what we call a high basicity slag. And the slag, you will remember, is what sits on top of the iron and comes out of the blast furnace separately. They used lime even with a charcoal furnace, because if you didn't put lime in your slag, then you tended to lose iron in the slag, and they didn't want that, so they always put a little bit of iron in, lime in. And the sensible way of measuring the lime content of your slag is this basicity, which is the ratio between lime and magnesia, which are both sort of, as it were, basic oxides, divided by the silica, which is an acid oxide. And this basicity gives you a very good idea of what the sulphur removal ability is. The higher the basicity, the more you will remove sulphur. The only problem with that is that the higher your sulphur, your basicity, then the higher is the temperature that you need to melt the slag. And the slag melting point is a very important part of the furnace operation. Now, take no notice of the bits of stuff around the side of this. The only thing that's important on this slide is the temperatures within in the furnace. And you've got basically two very important zones in your blast furnace. The first one is at the bottom, where you have to have a temperature obviously capable of melting your slag or making your slag sufficiently fluid. But at that temperature, which is around about 1500 degrees, shall we say, the air that comes in, the oxygen in the air that comes in, burns the coke and creates carbon dioxide. Now, carbon dioxide at that temperature is not the stable oxide of carbon, and as it goes further up the furnace, where there's an excess of carbon, it reverts back to carbon monoxide. And the carbon monoxide goes up the furnace until it gets to the point where carbon dioxide becomes the stable form of the oxide, at which point carbon monoxide can reduce iron oxide to iron. And that happens about 700 degrees centigrade. So you have this reducing zone near the top of your furnace, and then there's further cooling and out go the gases at the top. The thing about coke iron, or about coke in the blast furnace, was that it was much less reactive than charcoal, as a result of which you got a less steep temperature gradient within the blast furnace as you went up, which meant that the gases, as they came out of the blast furnace, were much hotter in a coke furnace than they were in a charcoal furnace for the same size and the same operation. And that, of course, was a source of great inefficiency. It was a great source of heat loss. But there was this issue that if it was very unreactive, then it would actually push the reducing zone out the top of the furnace, at which point you could no longer expect to get any decent iron out the bottom. And the best illustration of this, I think, is because it's sort of, you can deduce it from all sorts of things, but the best illustration, I think, is what happened in Prussia in the 1780s, when before they built their first coke iron furnace, they decided they would actually check that the coal that they'd got could be used to make iron. And they chose to do some experiments beforehand in a charcoal furnace at a place called Malapana. It's on the Malapana River. And they failed. The coke that they made did not actually work in the furnace at Malapana. They called William Wilkinson to come across, and he came across and said, well, it's very straightforward, your furnace is not tall enough for this coal. You've got to make a bigger furnace, otherwise you won't get your iron out. So they raised it from 25 feet, and this is recorded, to 30 feet, at which point it worked. And they then went on to build the Leibitz foundries, where actually the furnaces were about 40 feet high. But the point about this is, you have to have, you clearly need to have a coke. If you're going to use a 25-foot furnace, and the assumption has always been that Abraham Darby's furnace was 25 feet or less, may or may not be right. But if you were going to make your coke work, then you actually had to have as high a reactive coke as you could possibly get. And that was the reason why Abraham Darby specifically used the clod coal to make his coke. And here you have the comment of Charles Wood, who visited Cobra Bailey in 1754. He said, the coke from clod coal is near as light as wood coal. In other words, it's the next best thing to wood charcoal. But still, I'm pretty sure that they had to maintain a fairly low temperature in the hearth in order to keep that reducing zone in the right place. And I don't believe that the hearth in a coke furnace was any hotter than was in the charcoal furnace. The fact of the matter is you can certainly get a higher temperature in a charcoal furnace than you would get in a coke furnace at the time, because very often on the continent they found themselves using a high sulphur ore. And when they had a high sulphur ore, what did they do? They wound up the temperature of their charcoal furnace and put in more lime. So exactly reproducing what happened later in Shropshire. Now then, you can't play around very much with a blast furnace, whether it's fueled by coke or by charcoal. You actually have to get the conditions absolutely right, and basically the output for any given grade of iron is proportional to the volume of the furnace and to the height of the furnace. The efficiency of a coke-fired furnace, of course, depends very much on the height of the furnace. And you can deduce from what happened at Cobra Bailey that they progressively increased the height of the furnaces as the first half of the 18th century went on. Now, I've quoted here specifically the peak outputs, because output varied depending on how much water you had coming down the stream. And in the winter you had plenty of water, but in the summer they very often ran out completely and had to stop blowing the furnace. So Richard Ford, who basically ran the company between Abraham I and Abraham II, initially put in what's called a horse gin, it's wonderful, a horse engine, which pumped water back from below the furnaces into the pool. But at the same time, the peak output went up from 5 tonnes a week to 9 tonnes a week. And that suggests to me that they took advantage of having that extra availability of air to actually build their furnace bigger. And then when they installed a Newcomen engine, then in 1742, we don't have the figures either side of it, but by 1754, the output, this is according to Charles Wood again, was 12 tonnes per week. By which time, Charles reckoned that the furnace was about 30 feet high. So they had raised the furnace progressively. And the supposition is that once they were able to get to that sort of size, they could actually get a higher temperature in the bottom of the furnace. And so, when they built the first Horsay furnace, they got 22 tonnes a week out of it. The supposition is that it was considerably bigger, yet again, than the 30-foot high furnace of 1754. I have to say that actually, they're not strictly comparable, because Horsay was a furnace for specifically for making pig iron for the forges, and it was much easier to make pig iron for the forges because all you had to do was cast twice a day onto the floor and just carry on making iron. Whereas if you were making castings, a lot of the castings were made with the iron that came out of the blast furnace, and you had to sort of slow down the output of the blast furnace to get it. And you're also making a higher quality iron, that is, with more silicon in it, which again actually reduced your ability to produce more iron. But big nod to the Newcomen engine, because all these new blast furnaces in Shropshire were actually driven by a Newcomen engine. There wasn't enough water coming down any of the streams in Shropshire. There were some places where you could do it, and South Wales started without steam engines, but without Newcomen engines. But basically, the Newcomen engine was responsible for this great step. And just to risk of flogging a dead horse, Lothian Bell recorded a lot of the sort of performances of 19th century blast furnaces. You can see they got up to 48 feet, even to 80 feet, and the temperature of the gases was still going down as you increase the height. Whereas the exit of the charcoal blast furnace in Sweden at the time was considerably lower. And that the temperature of the slag of coke furnaces was 220 degrees higher than in a charcoal slag furnace. And just to emphasise it still further, these were the basicities that were being reported in Russia actually in the 19th century, where they had both charcoal and coke furnaces. And as you can see, the basicity had gone up, from the one that we were getting in the 18th century to 1.5, but the charcoal furnaces were still cheerfully working at a basicity of 0.6. I have to hurry up now. I'm sort of slightly making this one up, I have to say, but only to make a point. Henry Cort, most of you will know, I'm sure, invented two things in the 1780s. One was the use of grooved rolls to do what had been done with hammers before in the forges. So you had to beat out the slag from your first produced malleable iron, and they used to beat it out with hammers. Henry Cort was the first one to use rolls to do the job, which was a great advantage. And he also invented the puddling process. Now this is a reverberatory furnace, and I mentioned that this was used in the 17th century to melt iron, but Henry Cort used it to turn that iron from the blast furnace into malleable iron by taking out the carbon, and it was just done by exposing it to air to take out the carbon. Now, when he produced his first iron, it was fantastic. Because not only did he actually produce iron more cheaply than anybody had done it before, but he actually made a better iron. And he worked down near Portsmouth. His chief customer was the Navy, and the Navy, when they tested his iron from his puddling furnaces, said, "This is fantastic. We can actually use this to replace all this super iron that we've been getting hitherto from Sweden, the best Swedish iron." Fantastic. When Henry Cort tried to interest the rest of the world in this, the rest of the UK anyway, it didn't work so well. Produced quite a good iron, but it was enormously expensive to do so, and in fact it was rejected in Scotland when they tested it. It didn't immediately take on in the Midlands when it was tested here. The South Wales people, particularly Richard Crawshay and Samuel Homfray, tried to run with it, but they almost gave up. And I sort of imagine almost a telephone conversation between Homfray and Crawshay and Cort. So a bit of levity at this stage, you've got 5 minutes. So Henry says to Richard and Sam, "Well, you know, how are you getting on with my process?" And they say, "Well, it's not very good. It doesn't seem to work very well. You know, it just doesn't oxidise very easily. I mean, you know, we rake away and the liquid just closes up behind the rake, and when we're doing that, the sand bottoms of our furnaces start to erode away. And by the time we've finished it, you know, we've got a very expensive iron." And Henry Cort says, "What do you mean the liquid closes up around you after you put your rake through it?" Richard Crawshay says, "Well, doesn't it with yours?" "Well, no," he says, "my iron's not liquid. Mine's pasty." "What do you mean yours is pasty? Where do you get it from?" "Got it from the Navy." "Where do they get it from?" "They get it from the hulls of ships." "Oh. Must be quite old then, mustn't it?" "Oh yeah, it's been around for yonks. It's been, you know, at least a couple of shiploads at the time, you know, it probably came from one of the local furnaces. They used charcoal, didn't they?" "Yeah." "Well, I'm using coke." "Ah. Well, I don't know what we're going to do about that." Well, cut a long story short, they invented the refining furnace of running out fire as a pre-treatment to the iron, so that they turned it white, because the iron they had before was grey. And this explains why. I'm sorry I've had to eventually to introduce the iron carbon phase diagram, but the point is that measure that I mentioned before, the carbon equivalent, it wasn't designed in the first place to tell you whether an iron was going to turn out grey or white. It was actually designed to tell you where the eutectic was when you had a high silicon or a high phosphorus. So actually, whatever iron you had, the eutectic point always appeared at 4.3% carbon equivalent. And if you remember, all the ions that were, I mentioned for converting into wrought iron were less than that. And there is the explanation. When you're to the left of the eutectic point, you get a pasty mixture. You don't get a liquid iron at all. Whereas if you've got a grey iron, which is much nearer the eutectic point, it's actually truly liquid when it gets there. So that's the metallurgical explanation for Henry Cort's problems. And I've actually come to the end of it, but most of you know what happened to Henry Cort. He was very unfortunately treated when his principal backer, who was he was also his principal purchaser, committed suicide and owing a lot of money to the Navy, and Henry Cort was made bankrupt, and the Navy said, "Well, these patents are not worth a thing. We'll just forget them." Into the 19th century, the puddling process just about made every single bit of malleable iron that was produced. It built the ships, it built the railways, it built the Eiffel Tower, it built all sorts of things. And actually, the puddling process moved to Europe very frequently before coke in the blast furnaces moved to the same state. So, this is just to tell you that although Richard Crawshay had agreed to pay a royalty to Henry Cort, then Samuel Humphrey said, no, I'm not going to pay him the royalty, it's not worth it. And you can see, in fact, that Henry Cort's patent said quite specifically, you don't need to treat the iron before you use it. Just gone slightly past my date. I'll stop at that point if I may.
Thank you. Richard, have a seat. You made me feel intensely nostalgic. It reminded me of my scrap dealing days when we used to buy high silicon iron from Russia because we could free ride on the silicon, which is exothermic. And, I also now understand why charcoal blast furnaces that I've seen are really quite squat. So that's a very welcome insight. I'm going to ask Fred, Dr. Fred Starr, to open the discussion as an esteemed metallurgist, as a columnist in Materials World. Fred, the floor is all yours.
Well, thank you for giving me the opportunity of giving my personal thanks to Richard. There are very, very few lectures I come to for Newcomen in which I can say I am completely satisfied, completely overcome by what the speaker has said. I followed it. I do hope others managed as well. With a little bit of work, you will follow everything that Richard has said. Now, what can I ask in terms of questions? Well, you've done so well. I can't ask a question about what you've been talking about. I will ask one question first of all, which is off the board, which is, you sort of touched on it, in which you said, oh well, people realised that the grey cast iron could be used for things like cannons and steam cylinders and so forth, very early on in the 18th century. I think it's quite interesting that most metallurgists regard cast iron as being very brittle and not having any tensile strength whatsoever. Well, it has, and it enabled a lot of progress to be made in the 19th century with big structures. When did people begin to realise, my question is, when did people begin to realise that you could actually use cast iron, up to a point, taking advantage that it has got some tensile strength? That's my question. I also have another off the topic point, which is never really discussed, but me coming from the gas industry can make this. The thing which is never asked about is, what was wrong with coal itself? Why did they have to go to coke? Well, I can answer that, because British Gas in the 1970s came out with a wonderful method of making gas from coal. Straight coal in what was basically a glorified blast furnace. And the trouble with coal, they found very quickly, is that if you remember your time when you were a kid, when you threw coal on the fire, it goes through this sticky stage in which nothing gets through, it agglomerates and sticks together. One of the big inventions of British Gas was to actually put what was a glorified aeroplane propeller inside of the gasifier, which went round and round and round, stirring the whole thing up and enabling the gases to get through. Well, that's actually going to be forgotten part of technology, because the British gas gasifier has died, like a lot of other ideas of the 1980s. Thank you very much. But if you could answer that question about when did people realise that you could use materials, cast iron, grey cast iron, in a structural way, and what were the first big things that they did with it?
I'm not sure that whenever they got into really sophisticated structures, they were ever prepared to rely on cast iron in tension. The problem was that cast iron did have tensile strength, and people measured it. The problem was that, give it a bang, then the theoretical tensile strength was of no interest whatsoever because it was brittle. And so I think that things like bridges and so on, they never allowed it to go into tensile tension. But of course, it must have been in tension in a cannon when you fired a cannon.
Exactly.
It must have been in tension.
Exactly.
So it certainly would take it, but you have to be very careful because of this, the fact that it was so brittle.
Well, I did a little article for the Western Courier on this is following the trek to Teesside last year, when we saw some rails, which I thought initially were cast iron, U-section rails, and they were actually wrought iron, but I thought they were cast iron because the original type of rails were cast iron. I did some estimates of the strength, and it came out that the strength that was being asked for from the cast iron was 2 tons per square inch. And if you look at relatively modern accounts, that is regarded as a safe working stress for cast iron. So they must have known something of this nature. Certainly I would have thought by about 1770.
Well, they were certainly beginning to think about strength and measuring strength by the end of the 18th century. But I suspect they wanted to have a very wide margin of error because they weren't very precise with the way they were doing things.
Oh, Fred, follow up. Yes, you're free to
No. It's over to others.
Okay, I was just going to say how true your point about coke in a blast furnace, of course. The weight of burden is tremendous. So you need particularly strong coke to bear the weight of the burden while still being permeable.
Well, I was intrigued by the height of the furnace because when I worked on the clay lane furnaces at Dorman Long, I think those must have been round about 100 feet high, and they were using very, very hard coke, very well-fired coke, to take the burden. And that ties in with what you said about the stronger the coke, the bigger the furnace that you need, because you need more, the coke is not so reactive.
That's absolutely right. I mean, in the middle of the 18th century, in South Wales, where the coke was not very reactive, they actually deliberately built their furnaces 50 feet high, whereas in Shropshire they were still about 30, 40 feet high.
I won't digress on alkalis in Russian coke either. Let's throw it open to the audience.
Can I make a
Tim, go on.
point about the welding furnaces, which of course were all charcoal fired, yet they were happily producing a grey iron. Cannon is an obvious example, but things like grave slabs and so forth, and even salt pans they were making, which are relatively thin sections. So, and of course they had forges as well, so they were presumably producing a white iron, so somehow they were balancing the charge that they were putting in, presumably the charcoal to ore ratio.
Yeah, well, that would be it. They wouldn't have, I think, been able to produce an iron that would have made a thin pot in sand.
No,
but cannon, of course, you want a much lower carbon equivalent to get a grey structure.
yes.
It had to have less silicon in it, otherwise you've got a weak cannon.
And an interesting point that Fred brought up there regarding the cannon being tensile. The more expensive cannon had a process which they called kneeling.
Yes.
Not annealing, but kneeling.
This was Prince Rupert.
Well, and we've never really understood what this means, but it did seem to involve a long-term heat treatment, which of course would sterilise the flake iron. So I suspect they were doing that, and they were also turning them, which of course would then reduce any notch sensitivity.
Well, I think people have suggested that he was the first one to use what is now known as malleable cast iron.
Yeah.
But in order to do what he was doing, he would have had to cast a white iron first, and then heat treat it. And the white iron would then break down and produce carbon nodules to protect the carbon.
Yes, yes.
That was like, there's always the assumption that that's what he'd done.
Right, from a white iron.
Yeah.
Yeah. Thank you.
Questions at the back there? Yes, Stu.
Right, can you explain what the difference between coking coal and ordinary coal is, and why did Coalbrookdale have some?
Well, that's very interesting actually, because the coal that they used at Coalbrookdale wasn't a coking coal. A modern coking coal was one where it swells, and you basically the volatiles come off. You get actually a mass of solid coke coming out of it. It's sort of turned into one sort of mass. And that's the sort of classical understanding of what a coking coal is, and that's what happens now in the coking furnaces. But the clod coal that Abraham Darby used didn't cake, it didn't swell, it behaved just like wood and charcoal. So you put a lump of clod coal in your coking oven or a pile in the ground, and it would come out as a lump, having lost the all the volatiles and all the things that were carbon and ash.
Well, didn't somebody say, well, use my coal instead?
Well, eventually they did, of course, but the classic coking coal that you use in a modern blast furnace was much less reactive, so they couldn't use it in the small furnaces to begin with. So it sort of came along later.
Question at the back. Yes, please.
I think maybe you had your tongue in your cheek when you said that cast iron wasn't used in tension until the means of making fabricated wrought iron plate girders using rivets and so on was developed in the 1840s. Then most structural beams made in iron were of cast iron, right from the early days of the fireproof floors right through to early railway period. And I.K. Brunel was one of those who used it extensively for a bit until such time as the wrought iron came along structurally to supplant that. And so, I was doing research on A.K. Brunel's use of cast iron, and unfortunately I didn't find enough information to be able to relate to exactly why he was able to get it to work, or maybe he wasn't, he was just a bit optimistic, but he certainly had quite high factors of safety, low factors of safety, and I wonder if there's anyone who can help me along the metallurgical side of this history.
Well, I think they must have been much more confident of using cast iron in tension when they knew it wasn't going to be subject to any sort of dynamic forces.
Yes.
So if you put it in a building and use it as a beam, then okay, some of the beam would have been in tension, but it wasn't going to be given a bash. It wasn't going to get any vibration. It wasn't going to get a bang, which would make it fail. So I suspect they were much happier to use it when there was no dynamic load or anything. But as soon as you came to wanting a bridge with a train going over it, then it was a very different matter. And I don't know whether you remember not the Tay Bridge disaster, the D Bridge disaster. It was one of Stevens' bridges which failed, and they came to the conclusion that he'd actually misdesigned it so that some of the cast iron drifted into tension.
Julia, do you want to come in?
Just saying, because we were discussing it this afternoon, it's on the
Yes.
Chester and Holyhead Railway, most famous railway, iron railway collapse in the world. Wouldn't you say, Malcolm? the Chesterdean Bridge, and out of it came enormously more sophisticated. I mean, they really got to understand how it all worked after that bridge. I was moaning this afternoon because there's an article in Links, and it says that it was over the Dee in Llangollen. And I'm sitting there saying, no, it isn't.
Can I just add a bit
Tim, yes,
to
sure.
that as well? Of course, Brunel started using cast iron bridge beams, but he had a failure over the Uxbridge Road where the train had derailed and caught fire, and it was the actual thermal expansion apparently that caused the collapse in that place. And then he wouldn't use cast iron in tension after that at all.
It was the actual what? I didn't catch that.
There was a train that got derailed and then caught fire.
Yeah.
So it was actually the fire rather than the impact of the train getting derailed that caused the bridge to fail. It failed over a period of time in the balance.
There were in fact two failures of that bridge. It's a slightly more complicated story.
Tell us if it's a more complicated story.
Well, I don't want to tell you at the moment, but eventually they did rebuild it in wrought iron, but when it failed first, before the contractor had handed it over to the client, and it failed, I don't think there was a fire on that occasion. It just broke, and Brunel blamed the contractor and made sure that the replacement beam was made more carefully than the one before.
That sounds typical Brunel.
Yeah.
John, sorry.
To pick up this problem about tensile strength in cast iron, certainly by the 1780s you are seeing written evidence that people understood the problem about the fact that a beam is both in tension and compression. And they understood at that point that the only way to make a beam that would work is that the section of the beam which is in tension had to be made much, much larger than the section that is in compression. So this is why you end up with these beams where you have a small piece at the top coming down the web and then a very, very large bottom. The problem comes then is that really beams are used in two situations. In a building, the load is substantially static. You apply the load and it doesn't vary. If you take it into a bridge, it is not just the risk of impact loading, but the fact is that every time you go over it, you get fatigue loading. This was realised very, very early on, certainly by the 1820s. The Dee Bridge was an attempt to get around both the impact loading, the fatigue loading, and the problem of casting very large sections, where they put into it some tension members as well. The problem is you couldn't distribute the forces between the tension members and the non-tension members equally. So it was a very, very complicated situation, and they understood it very clearly and very, very much earlier than people realised. The problem was that the engineers that came along, the railway engineers, made very, very poor use of the founders. The founders understood it, but it wasn't until the engineers, and Brunel was a classic example, he would have listened to his founders, at that point that they then started to get things. Of course, by that date, the Dee Bridge had failed, wrought iron was on the horizon, and so basically everybody went to the safe approach, went back to the arch bridges to wrought iron.
Gentleman over there, yes, please. Having been talking about the Iron Bridge Gorge Museum and so on, could you just place the Iron Bridge in its historical context of this type of iron?
Yes, and the interesting thing about the Iron Bridge is it's a much thicker section than a pot, and they did construct the Iron Bridge so that it was always in compression. I think if you look at the design, you can see that it was always in compression. But the interesting thing to me was that they actually varied the silicon content of the iron so that it was right for that section size. They somehow knew that that's what they needed. So they, what I talked about having the right silicon content for the particular section size was, they knew about it, and that's what the iron, went into the.
So it was basically a cast iron bridge.
it was it was substantially all cast iron. There were some wrought iron members that were there, bars that were taking up some of the tension.
Fred, do you want to come back?
Yes, I was particularly intrigued by what you said about the white cast iron and quartz process, and the fact that you've got in that liquidous area a mixture of austenite and liquid graphite on the other side. You've got some very, very interesting tribological issues. I don't know whether you've come across this paper by some Canadians who looked at the puddling process, the later version of it. They looked at the thermodynamics, but they also looked at the flow properties of the material in the process of actually producing the steel balls. What they didn't do is look at what would have happened if you'd had grey cast iron. Have you had any contact with these people?
Well, with the chap in Canada?
Yes.
It wasn't a chap by the name of Raider, was it?
I think so.
Yeah, well, Raider's dead, unfortunately.
Oh, I see.
Whereas I take him to task over a lot of the things.
Seance is called for.
Find a good medium.
So where did you disagree with that?
Well, he wrote a lot about the reactivity of coke and what it meant. He was one who came out with the idea that the coke-fired blast furnace had to be hotter than the charcoal.
Oh, this is on the puddling process.
Yes, I didn't know he'd actually written a paper on the puddling process.
Well, I can present you with it.
Well, that's right. You think it is by Raider, then? R-E-H-D.
I've got a terrible name for that, terrible memory for names. But I'll give you the paper afterwards.
Well, thanks, yeah. He was Canadian. And there was the sort of thing he did. He wrote a book on the use of fire in antiquity and things like that. He was a foundryman, actually.
Yeah.
Frank?
Thank you. I'm fascinated by the way in which they managed to put the right amount of silica in a beam for the iron bridge, for whatever particular beam they needed to use. How did they actually calculate that? I mean, is there any documentary evidence leaving where they sort of actually calculate? This is actually fairly sophisticated sort of chemical, metallurgical work that they're doing. So I would have thought there must be some sort of...
But you remember those bars I showed that they found at Sawdust?
Yeah.
I think they must have been able to tie the quality of the iron they got with the way they worked the blast furnace.
Mm-hmm. They must have written it down, surely, somewhere.
Well, nobody's ever written that sort of thing down. No. It's you know, they must have worked it out, and it was probably a skill that the founder kept to himself, if anything. Yeah. When it came later in the 18th century, John Wilkinson, when he started making his cannon, he actually, I don't know whether he used wedges or something, but he used to make himself a grey iron in his blast furnace, and then he'd remelt it in a reverberatory furnace, and he would deliberately oxidize out the silicon. So he'd start with a high silicon, and then he would bring the silicon down until he's got what he needed to make these cannon. And he must have had a very superior control system for working that out. Now, whether he used that sort of test wedge that I showed, which he could have done, there are other ways of doing it. But something like that must have happened, I reckon.
This gentleman front row, then David. Yep.
This question isn't really about metallurgy, although it is about myth and the different temperatures of charcoal and coal. Britain made white sparkling wine before it was made on the continent. And the story that I've heard, which I'm not quite sure is true, is that we were able to do it because we had stronger glass, and the glass could withstand the pressure of the fermentation inside the bottle. And the reason we had stronger glass is because we were forced to use coal rather than charcoal because we had a shortage of trees. And the coal burned hotter, and that's what gave the glass's strength. Can you tell me whether that's a myth that's...
If you really wanted to get a relatively small object very hot, then the best thing you could use was coke. Because the coke was denser, you could pack it into a smaller area, or you could pack a greater weight into a smaller area. And then if you blasted it with air, you could really get a very high temperature. And that was how Huntsman managed to melt steel in the 1740s, by packing coke around the crucible and really giving it a huge blast of air. So you could make coke as hot as you wanted to, almost, within that region. But not in a blast furnace that was only that height.
Right.
Because that was the question, then blowing, as it were, the reducing zone out the top of the furnace.
The story is credible, you think?
I think the story probably is credible. People used coal for making glass in the 17th century. It was one of the first things, Peter, wasn't it? That was
1615.
Yeah. That's already being substantially used.
But I mean, the other thing with glass you need to remember is that how it behaves will depend on how well you've annealed it to a certain extent, and so it's not necessarily the temperature it's been up to, but the regime by which it came down to room temperature.
So it's slower being stronger, I presume.
Yes, I mean if you get it, if you chill it completely, just make something and then let it come down very quickly to room temperature, you'll touch it and it'll shatter. You've got to slowly cool them down, and so I think it's probably the cooling regime rather than the heating regime which is what gives you more or less robust glass.
Thank you, Justine. Perhaps we should get you talking on glass. That's the way forward as the follow-up. David.
My question is, looking at some of the tables you produce wouldn't stand up to modern scientific analysis. There's no error bars, there's no plus or minuses or anything like that. And really, the product that comes out at the end is in all chemical reactions, and they're only chemical reactions, is only as good as the materials you put in and their variability in the first place. And there seems to be, coke, it must be so variable. And certainly in the 18th century, it must have been exceedingly variable. I just don't know actually how they got anywhere near saying, well, we're going to produce this kind of iron. I really don't.
Well, it was interesting because in the 1750s, there was a bit of a legal case between the Cobra Bailey company and actually maybe a bit before the 1750s, a legal case between the Cobra Bailey company and their landlord, because the Cobra Bailey company was not taking as much of the coal from the landlord's area as they'd basically been contracted to do. And there was a big court case, and the answer from the Cobra Bailey company was that this coal, it's clod coal, but it's not good enough for us. We had to use a very special clod coal, not just the clod coal, it had to be a very special one. So they were pretty careful.
Yeah, but clod coal must vary. It can't,
well,
it can't be 99.99%.
No, of course not. But they didn't just use any old clod coal. They had a pretty good idea of what they needed to use.
And what you say applies with equal force to the iron ores too.
Yeah. Oh, yeah. And the silicates and everything. Put it. Yeah. It really is.
That's amazing. They made.
And how did they do their, what I say, even in Victorian times, their basicity calculations?
Well, they didn't just the answer there. They just knew how much lime they put on the top.
So we've got tables showing us basicity calculations that probably couldn't have been made.
They weren't made at the time. No.
It's the experience of the workman.
Yeah.
I mean, it's the same.
Experience of the
didn't
founder.
have my, metallography.
So you're saying they're accumulating tacit skills, it's a black art, they're keeping it to themselves, and they might have intuitively known a great deal more than was ever recorded. That's the point you were making.
Yes, sir.
Dan and this gentleman here and then Dan.
That's what I was just thinking, you know, base level, you're just sort of underestimating their skills. I mean, most skills like that years ago, I mean, the eye, sensing these things would have been that was their trade, wasn't it? These people weren't, you know, they didn't have to sort of go and send that to the lab to get it sorted out. These guys would look at something, and the way it was performing, the colours and things like that were coming off, that's their skills, isn't it?
Mm.
So I mean, you know, that was, and they were few and far between. That's why they got names, these people, wasn't it? Really?
Well, that persisted into the open half days, didn't it?
Yeah.
Well, that was the point I was going to make, that I saw people in my time, this is 1960, when we were doing very rapid chemical analysis, using test bars. You take a little bit of steel out of the furnace and you put it in a mould, and then they hit it with a hammer, and that told them how much carbon you got. Well, they could do exactly the same with the kind of castings that you're doing. I guess that some of the things that you showed from America might well have been of that type, you know. You cast them with that funny sort of shape, you hit it, and where it broke and what the fracture looked like would tell you whether you're into the white, mottled or grey.
Absolutely, yeah. That's what they did. Exactly what they did.
I mean, nobody's disputing the skill of these people because they're clearly enormously skillful. What is interesting is how they acquired that skill and how they then transmitted that skill, and that's not obvious to me, I have to say.
That's true of all tacit knowledge, of course.
I suspect that the answer to how they acquired the skill is that they made an awful lot that didn't work.
That was the eye.
Yes.
You know, trial and error often means more error than...
Oh yeah, of course, yeah.
So speaks a plane maker. That's very implied.
We have... I could take you back to George Cayley in the 19th century, the 18th century rather, 19th century, saying, you know, we have yet to ascertain all the possible causes of accident, but until we do, at least 100 necks must be broken. We learned a lot by error in the aviation business.
And I think that's a very sanguine note on which to end. I'm sorry we've got to end the discussion, not least because I've got loads of questions to ask you, but I have the privilege of taking you to dinner afterwards. Just to say that those who wish to join us for dinner, we've changed from our usual venue, which is being refurbished. We're actually at the Scoff and Banter on Cromwell Road tonight, so I just mentioned that. But the other thing to say before I sum up and thank Richard is that the next meeting, the 12th of February, will be the AGM. That's being followed by Dr. Nina Baker, who's going to talk from airships to the space race, some women and their engineering achievements. I hope they'll mention Clive's late wife, since she is one of the key people in the engineering achievements in the aerospace business. But that's the next meeting here on the 12th of February, which is also our AGM. But returning back to this meeting, we'd like to thank Richard and his spectacular props. We'd like to thank Richard very warmly indeed for a splendid evening, and you, the audience, for an excellent follow-up discussion. Thank you very much indeed.